Hello everyone, so welcome to this talk, which is about analyzing the resilience of software composition analysis against the container image obfuscation. So today with me there is Jacopo.
Hello everyone, I'm Jacopo. I'm a PhD candidate at Aalto University, and at the same time I'm working as a researcher at the CNAM Institute in Paris. My research revolves around container and network security.
And my name is Agathe Blaise. I'm a research engineer working at Thales in France, and I'm especially working on the security of virtualized network environments. So very brief advertisement before we dive into the technical content. So this project was partially funded by a project which is named Sec4AI4Sec. It is a European project. So I put the link and QR code here. If you're interested in what we are doing, please check it out. We are always looking for collaborations. So now diving into the content of this talk, which is obfuscation in container in image. Why should we care in the first place? So 2 years ago at KubeCon 2023, a talk introduced the concept of what we call malicious compliance and container obfuscation. So starting from a base container, the presenters progressively introduced some modification to a Docker file and ultimately reduced the number of vulnerabilities that were found by open source tools. So they actually fooled the container vulnerability scanners, and which are in charge of detecting package and vulnerabilities in the container image. So in this work, we wanted to analyze how the landscape evolved over the past 2 years, and we proposed an academic approach to the problem that we will detail right after. So I will first give a short overview of the tools that exist for container vulnerability analysis and scanning. So there are typically two main steps when we want to scan for vulnerabilities in a container image. So first, this tool will index the content of the container image. So they will analyze the container file systems and try to find installed software. So it can be the operating system packages, the programming language, the dependencies and libraries, and finally the binaries. And at the end of this process, they will generate a software bill of materials, or SBOM, that is a list of components, all of packages running into that container. Then the second step is to search for vulnerabilities in this software. So they will match those packages against a base of known vulnerabilities. And typically, they leverage custom online sources and aggregate them together. Here is an example to find installed software using SIFT, which is an open source tool from Ensure. We analyzed a Python 3.10 image and output the result as a SBOM for JSON. So here is a list of artifacts that you can see. We have a list of packages. Each package is uniquely identified using a notation. We have the Common Platform Enumeration, or CPE, and we have the package URL or Perl. So those notations enable to give a unique identifier and to give details like the package name, the organization, the version, and even the author or distribution. So they also provide the path of the file that were used to find the given software, the layer ID where the file is, and finally some metadata information on the package. The second step is to search for vulnerability. So here we use Gripe, which is another tool from Ensure, and it will process the SBOM previously generated. So on the left, you can see the list of packages that were previously identified with their version and the type. For each package, you have one or several vulnerabilities, mostly expressed as CVEs with their severity and fixes, if possible, to upgrade to a newer version. So we can wonder which files are actually indexed to find those packages. And actually, there are different kinds of files corresponding to different types of packages. So first, we have the operating system, and it is mostly explicitly written in a file, like etc os release. It can be different files depending on the distribution and on the operating system. Then we have the package installed via the package manager of the OS. Here is an example to find dpkg package for Debian. Concerning programming language, we have the dependencies and the files installed via the package manager. So requirements.txt for Python, package.log.json for Node.js. And with the package manager, we have distinfo for Python and node modules for Node.js. And finally, we can retrieve some information about the binary. So how these tools index this content from the file system? By default, they will analyze the squashed representation of the container image, meaning they will combine all of the layers together to produce the final file system. And then they will search for known file names containing package-related information, just like the one that we saw previously. And they will use regex-based search for license, package version, author, and so on. So we can wonder what happens if some of these files are removed or even do not exist. One example could be that a developer did not use the package manager to install dependencies, but it downloaded software from source and compiled it locally. So in this case, we don't have all of the files to do the analysis. We also have meaningful content that is not indexed and not used by container vulnerability scanners. So we can think of the path of the file, which are not fully analyzed. We also have some content files, which is related to the package, like the configuration files, the binaries, but not actual package metadata. So those files currently are not analyzed. We have the history or Dockerfile comments, where we can see, for example, the URLs that were used to download software. And finally, we have intermediate layers that may contain very interesting information, so typically files that were previously removed in next layer of the container. And from this observation, we now give a definition to the concept of container obfuscation. So obfuscation is the act of intentionally or unintentionally modifying or generating the content of a container image, so when designing the Dockerfile, in such a way that the installed software is partially or even totally undetected by the container vulnerability scanners. And this can arise for several reasons. As we see, developers may want to reduce or to minimize the size of the container image. So to do so, they can remove installation folders, or it can be also the case when using custom software installation without using the package manager. And finally, using multi-stage builds. So we have several intermediate base images in the container when we copy only some of the files, and we can miss important files to do the analysis. And those are actually best practices and good guidelines when we write the Docker file, but at the same time, they make the tools vulnerable to obfuscation and the container image obfuscated. So from this observation, we derive a list of objectives that we would like to cover during this presentation. And in this work, we make the assumption that the container obfuscation is only unintentional, meaning it is not introduced by purpose and for malicious intents. And first, we want to understand what are the main types of obfuscation and how they occur. Then we will study different state-of-the-art tools to see whether they are vulnerable to obfuscation. So we look both at cloud-based and open-source tools. We also analyze real and popular container images to see whether they actually contain obfuscation and may be deployed in production. And finally, we propose countermeasures and mitigation to avoid container obfuscation when building the images. So now I will give the floor to my colleague Jacopo. He will present you the objectives and the work we've been doing to answer them.
Hello again. So let's start our journey towards container obfuscation. First objective is to derive a taxonomy of the different obfuscation techniques. For that, we explored different information sources, starting from research papers in academia, then white papers, industry standards, and we even went into open source software and looked at the source code and how they work. We then built a taxonomy of the different type of techniques that can be used to obfuscate the content of a container image. And here is the list of 8 techniques that we were able to devise. Bear in mind that all of this assumes that the creator of the Docker file has a non-malicious intent. So first tactic is the OS obfuscation, meaning that users can delete, modify, or somehow alter the content of the files containing operating system information. Then we have OS package information, where basically users, they alter the content of the databases or files that contain information on the installed dependencies. Similarly, we have dependency obfuscation. This time we talk about programming language dependency files. Let's say requirements.txt for Python or package.json for Node.js. Similarly, we have package obfuscation. Package obfuscation happens when a user downloads dependencies and then alters the content of the downloaded dependency. Let's say changes the content of the node modules so that the version information or author information of the dependency is altered. Then we have URL obfuscation. Basically, the user downloads software from the internet rather than using package managers. Then we have alias and link obfuscation. In this case, we use aliases or links to hide the path, the real path of some files that are used as index files from software composition analysis tools. And finally, we have the pack obfuscation. Basically, the content of the image is compressed. So this refers to multi-stage builds or tools that compress the layers into a single one. So now that we have a taxonomy of the different obfuscation techniques, the next question is obfuscation detected by state-of-the-art tools? So we need to find out whether these obfuscation techniques can be actually exploited by an attacker. So for this, we selected 6 different tools, ranging from open source tools to cloud ones. So here we have CNCF projects like Trivi, but also open source tools like Sift and Gripe. We also have Docker Scout, Artifact Registry for Google, Defender for Cloud in Microsoft, and Amazon Inspector. Okay, now we have tools. We have techniques, how to test them. We need to generate a data set of images that are increasingly obfuscated. So we curated a data set to test the resilience of tools to obfuscation, and you can find it here. There's a QR code. So we started by a base image, base Python 10 image that is not obfuscated, and then we started progressively adding more and more obfuscation techniques. First, individual techniques, and then we combine multiple techniques in the same image. And here are some of the results. So as you can see, many tools, actually, can I use this maybe? Hello? Does it work? Well, anyway, yes. So as you can see, many of the tools are vulnerable to individual instances of obfuscation, but then as more techniques are combined, the tools become more and more vulnerable to them. So what we decided to do was that we decided to check for vulnerabilities and packages detected for each tool and technique, just to have a more comprehensive overview. So here's a table that shows for each technique and for each tool the number of vulnerabilities and packages that are found. And we can see also that the impact of obfuscation increases also here with the number of techniques. And we can see that for many tools and many techniques, we have 0 vulnerabilities and 0 packages identified, meaning that we reduce quite a lot the visibility of this software composition analysis tools. But we also see something else. You see on the right here, you see not available. This is because some of the cloud tools, they actually make assumptions on the content of containers. So if containers do not have a specific file or specific files, then they will refuse to scan them for vulnerabilities. And many times it's very hard to distinguish a container that cannot be scanned from a container that has no vulnerabilities in the UI. Also, food for thought, as you can see, tools report different numbers of vulnerabilities and packages, and sometimes tools may recognize for different type of obfuscation the same number of packages but different vulnerabilities. For instance, SIFT for the OS obfuscation finds 9 vulnerabilities, but for the alias obfuscation finds 625. So to sum up, the key findings are that there is a significant impact of obfuscation across multiple tools. Every tool has at least one, is vulnerable to at least one obfuscation technique, and that cloud scanners reject at times images that are missing some specific files. Let's now go to our third objective, obfuscation in the wild. So now we know that obfuscation exists. Tools are somehow not resilient to it, but are containers in the wild using obfuscation techniques? So for that, we first decided on a data set. We had to find containers to scan. We selected 6 different data sets because we wanted to cover as many use cases as possible. So are obfuscation techniques happening only in hobbyist container images, or are they available in production, or do we see cases in production? So we selected Docker Hub official images, Docker Hub Bitnami images that are very popular for hobbyists and in the cloud, Docker Hub verified, open source software, and then the Quay.io registry and the official Amazon ECR registry. Okay, how to detect obfuscation? We devised a methodology to effectively detect cases of obfuscation in containers. So how this works is that we take the container image and we do 2 things. So first, we extract the image layers, and at the same time, using the OCI standard, we are able to reconstruct and extract the metadata information on the original Docker file. With the container image layers, we basically generate a sort of a Git repository by looking at all the modifications and changes on each individual file. And then for the Docker file, we instead look at instances where software is downloaded from the internet. And at the end of the day, if we see software downloaded from the internet in the Docker file, or we see that files with a known file name, let's say requirement.txt, changes or gets deleted, then this is a hint for us that the container was modified or was obfuscated. So we have a data set, we have a methodology. Let's test this 600 containers and see what happens. Okay, this is a global view across the different containers. And these are all the different cases of obfuscation that we find. So we see that more than 10% of the containers, they present OS obfuscation. Most of the times, they modify the OS information, but sometimes the OS information is also deleted. Then we see a spike on the OS package, and that is because mainly most of the containers, Docker files, they run apt-get update as a first command. But however, we cannot really remove them from this count because in many other cases, the upgrading the dependencies also comes with installing a software from source. Then we can see that there are many containers that are downloaded from the internet, like 20% of them, and also package and dependencies are removed. Then we computed the same results, but we grouped them by dataset. And those are the observation that we see is that obfuscation is present in all of the containers, so all of the registries. So it means that there is a small but not significant difference in the amount of obfuscation from hobbyist to production grade containers. And also we see that Bitnami has a surprisingly low number of OS and OS package obfuscation, and this is because Bitnami packs all the layers inside one using a tool called Crane. So we basically don't have a view of the changes in the file system. Let's now see a practical obfuscation attack. This is an extract from a very popular Docker file for PostgreSQL. As you can see, there is a really large run command that first installs all the dependencies, then downloads some software from the internet, then it also installs plugins for Postgres, and then builds the software and then downloads everything. So what it means is that the corresponding layer will just have a couple of binaries, and one of them would be a Go binary, which is okay. You can actually get the dependencies, but the other one is going to be a C binary, and it will not be recognized by any software composition analysis tool. So how can an attacker leverage this? Well, basically, the attacker will just wait that somebody creates this container or will just downloads the container, and then it will actually check that it will exploit known vulnerabilities on this image, and one of them is the CVE 2024-10-979, which allows an unauthenticated or unprivileged attack to the PostgreSQL container. So basically, the external attacker will just gain access leveraging this CVE, and no CI/CD tool will report this vulnerability. Good, but can we actually mitigate instances of obfuscation? So we know that obfuscation exists. We've seen several cases of obfuscation in open source containers. How can we mitigate it? So we kind of borrowed some of the ideas from our first methodology, where we were able to identify cases of obfuscation. And basically, at the fourth step, we do an iterative analysis of all the layers and the reconstructed Docker file. And we basically examine each layer individually. Then we analyze package metadata and the actual downloaded packages. So not only the requirements.txt, but we go in and we look at every downloaded dependency. Then we also analyze binaries, like Go binaries, configuration files, libraries. And we also look at the file paths. So we try to somehow increase the coverage on the container file system. So we use coverage as a metric to understand how well we are able to reconstruct the content of the image. And we built an open source tool called Orca, which is available here, and feel free to check it out. So those are the results of our tool. Basically, we are this methodology is basically resilient to many instances of obfuscation, way more than the state of the art. But still, you see that there are some cases of obfuscation that cannot be reconstructed, and that is because of the data loss that occurs when you use multi-stage build or when you compress the content of an image. We're getting close to the end, so these are the takeaways of this presentation. So container image obfuscation is still very much a problem in 2025. Obscure images are spread across multiple use cases, from hobbies to production deployments. We built a tool to discover and mitigate many cases of obfuscation, but not all of them can be mitigated. We have seen that multi-stage builds, compressed images, they actually make it very hard for any tool to discover obfuscation. So we need to update the best practices that we have, because we've seen an unbalance between the image size, so what people are trying to do, reduce the image size or reduce the instances of CVEs that are related to a given software. But on the other side, we have to think about the ease of scanning. We need to be able to provide new techniques and new best practices to make it easy and more transparent to build containers that are easy to scan. With that, we thank you. And if you want to check out our tool, it's there. And I think we have a couple of minutes for questions. Thank you. Okay, questions?
I think we can use this. My question is, while doing this research, have you ever seen cases where, for example, the file, like the requirements.txt, is saying one thing, but then actually, while doing with the other scanning techniques, it's actually something else? So it is like a sort of obfuscation, but it's saying that it has certain certain packages, but actually has others?
So the question is, have you ever seen cases where the content of a dependency file is different from the downloaded package? Actually, we have seen cases of that. We have seen mostly cases where the package, the requirements.txt is updated in a subsequent layer, so the user loads two different requirements.txt, or cases where there is no version pinning, so one version is basically the version on the requirements.txt may be vulnerable, but in the end, the version that is installed is not vulnerable, or the opposite. Yeah, that we have seen. Thank you.
Hi there, thank you. Great talk, by the way, I loved it. I have a point of understanding, because I'm not very familiar with SIFT. What's the difference between the columns of SIFT and SIFT all, because there were very stark differences?
Yes, Agathe?
Yeah, I can understand. So here, SIFT all is so SIFT is the only tool from the tools we analyze that allow to scan every layer independently, rather than scanning the squash representation of all of the layers. So that's why it's performed significantly better than other. So this is a good recommendation that we can say to increase the performance of the tools. And the only difference is that Orca can also analyze the URL downloaded compared to SIFT all.
Okay, thank you very much.
Hello, thank you for the talk. So you had the table with vulnerabilities and packages identified for each tool, and there was quite a wide difference in results across tools. Firstly, did you check kind of accuracy or differences across these tools and quality? And then secondly, how does Orca fit into this table? Does it identify packages and vulnerabilities, or does it fix the SBOM and then you would feed that to Trivy or something like that?
Maybe I can. So there are multiple questions here. First question is about the difference in packages and vulnerabilities across tools, and then the second question is about Orca, how it performs. Okay, really quickly because we're running out of time. So with respect to packages, we didn't do this work of actually understanding which is the source of truth. So which one of these tools has a good representation of the content. That's actually what we want to do research next. So we would like to find a benchmark of containers for which we know the installed software and see how it compares with across the other tools, basically, because we don't have a clear idea of what is the content of a container image in the first place. So unfortunately, I have no good answer on that. But for the second question about Orca, our idea was mainly to work on SBOMs. So the output of Orca is an SBOM that then can be ingested by other tools. Then, of course, there are problems also there because there's incompatibility between SBOM formats. But we made it sure that it was compatible at least with the SIFT, so that you can use it with SIFT. Yes.
Okay, awesome. Thanks.
You're welcome.
Great talk, thanks. My question is on a developer point of view. So as a developer, some of these obfuscation, I say, oh, I'm doing it in my Dockers and I can do it. Do you have a set of guidelines so me and my team can prevent doing this obfuscation like unintentionally on our Dockers images?
Okay. So the question is, do you have a set of guidelines? We have ideas on what to do, but this requires a community effort. So I can tell you, don't use multi-stage builds, and everyone here would say, oh my God, what is he saying? Well, there's like a balance between easy to scan and best practices when it comes to sides. So the idea is basically do not delete anything, leave everything as is, and this is kind of an initial step, but then of course you will end up with gigabytes and gigabytes of images. So it kind of depends, for sure. The idea would be to use our tool to find out if something is wrong, and then start from there and modify your Docker file habits. But we hope that in the near future we will be able to publish some real guidelines on how to make it easier for tools to scan containers. Thank you.
Thanks.
Hi there. One understanding question about the Bitnami images. So they came out with quite a few obfuscations, and you said that it was because of the compression that they use. So did they obfuscate the obfuscation with that? Is that what the outcome of that is?
So if I understood correct, the question is why is so that Bitnami container have less obfuscation? Yes. Well, the problem is that during their CI/CD process, they compress the content of the image. So the image has only one layer, and we cannot reconstruct what happened to the image, basically. So we cannot say whether or not they're more obfuscated than others because they just compress everything in a single layer. So we could only get information from the original Docker file, and that's it.
Great, thanks.
Hi, thank you for the talk. Just thinking about not using multi-stage builds, I feel like that's a pretty heavy cost that a lot of people aren't going to want to swallow. So is there maybe a middle ground where we could standardize a technique where when images are built, some sort of metadata is added to the image on the way, like as to what was in the image? Would that be like a better approach, or is there like a middle ground we can aim for?
Yeah, I think it would be a good practice because it's important to reduce the size of the image, also to reduce the surface of attack, but still by providing important metadata information about what is actually present in the image. So the objective would be to get a good balance between the transparency of the containers and the same way reduce as much as we can the size and vulnerabilities in the image.